Okay, good day. This is Math 130 Intro to Statistics. I'm Professor McCulley, and this is lesson number 21, hypothesis testing for the mean where the standard deviation is known. Let's get right to it. So, first thing, our goals, we're going to use p-values for z-test for a mean where the standard deviation is known. And we're going to find critical values and rejection regions in the standard normal distribution, and then we're going to use rejection regions for a z-test when the mean is known, and we'll also use p-values as well. So first, let's get some definitions out of the way. The z-test for a mean is a statistical test for a population mean. The test statistic is the sample mean, and the standardized test statistic is the z-value. And we've seen this before. That z-value is the sample mean minus the global mean divided by the quotient of the global mean over the square root of the sample size. And we must have these things being, these conditions being met before we can do it. The sample must be random, and either the population is normally distributed or n is greater than or equal to 30. I think that's spelled wrong. Let's spell that right, and we'll click Save. All right, moving forward. And then if you recall this right here, this expression here, this the um, lowercase sigma over the square root of n is the standard error for the sample means. Okay, so some guidelines, and these are the guidelines that I'm going to follow as I go through, and I will tick them off as we go through. The first thing we got to verify is that the standard deviation is known and that the sample is either is random or the population is normally distributed or n is greater than 30. We're going to state the claim mathematically and verbally. We're going to identify the null and alternative hypothesis. We'll specify the level of significance. We'll find the test statistic. We'll find the area that corresponds to Z. We'll either use the table or the normal CDF. I'm going to use the normal CDF. We're going to find the p-value. And then for a left tail test, we'll find the area of the left tail. For a right tail test, we'll find the area of the right tail. And then for a two-tailed test, we'll find the area of the standard test statistic. Make a decision whether we're going to reject to reject the null hypothesis, and then interpret the decision in the context of the original claim. So I've got two examples here. First one, auto racing. In auto racing, a pit stop is where the race car stops for additional fuel and tires, simple repairs and adjustments. The efficiency of a pit crew can greatly influence the outcome of a race. McCulley Racing Crew claims that its mean stop time for fuel and 4 new tires is less than 12 seconds. After a random sample of 30 pit stop times, a sample mean of 11.9 seconds was recorded if it is assumed that the population has a 0.2 second standard deviation. Is there enough evidence to support the claim at a 0.01 level? So first thing, let's go through those. Give me my pen here. Why are you not giving my, there it is, sorry. Pen. First thing we must verify that that is known. And in fact, they say that the population has a 0.2 standard deviation, so we can say that that is certainly equal to 0.2. And then n is greater than or equal to 30, and so they don't say anything about normal distribution, but since our sample size is 30 or bigger, we don't have to worry about that. Number 2 says state the claim. This should be known. Sorry. All right, state the claim. So our claim is that the mean, probably should make that capital, mean pit time for fuel and 4 new tires is less than 12 seconds. All right, so our null hypothesis and our alternative hypothesis. Let's see here. Less than is an inequality, so we're going to say that the mean here is less than 12 seconds. That is our claim. And we'll also then say that our null hypothesis has to be the complement of this, so mean greater than or equal to 12, and we'll go with that. Number 3, specified confidence level. We have an alpha equal to 0.01. And let's see here, number 4 says find the test statistic. And we have z equal to x bar minus the proposed mean over the standard deviation divided by the square root of n. In this case, we have an sample mean of 11.9. 11.9 minus 12 over the standard deviation 0.2 over the square root of 30. That, if we pull up my graphing calculator here, let's clear this stuff out, open this up a little bit here real quickly. Alpha y equals, we'll do a fraction there. It on top is 11.9 minus 12, and then we need a fraction in the bottom again, so alpha y equals 1, and then we'll do 0.2 divided by second x squared. Oops, do that. Delete that. We need a 2 there. There we go. Second square root 30. There we go. And we get negative 2.786, or excuse me, 36. So this becomes negative 2.7386. That is our test statistic. Now, we could compare that to a p-value if we wanted to. And again, the way that we could do that is number 5. We could do the inverse, or excuse me, not the inverse. Oops, I don't want that. Sorry, hit the wrong button. I need to clear this out. All right, so we want to compare this to our level there. And so what we end up doing is we're going to do the normal CDF. And we're going to go from negative infinity, or in this case 10,000, to negative 2.7386. And so graphing calculator, second, distributive, normal CDF 2, negative infinity. Our upper is, let's see here, 2, or excuse me, not 2, negative 2.7386. Our claimed mean for this one, because we did a standardized test statistic, is 0, and our standard deviation would be 1. We'll hit paste, hit enter, and that gives us 0.00308, 0.00308. All right, now clearly, so for number 6, and this isn't the only way that we could do it. We can calculate this. We could also, we don't necessarily have to find the test statistic to do this. We could go normal CDF. We could go negative 10,000. We could use the proposed mean of 11.9 versus, or this is our sample mean, and the proposed mean is 12. And instead of standard deviation, we could use the standard error. So we could go, just type it in, 0.2 divided by square root of 30. This will also produce the same values. And okay, and so if we go second, and then we'll we'll do normal CDF. This time we're going to go from negative infinity to the sample mean, and then this will be our proposed mean of 12, and our standard deviation won't be 1, it'll be the standard error. So we go 0, 2, oops, don't do that. It's 0.2. There we go. Divided by second square root 30, and if we put that in, we should get exactly the same, and we're close out to 4 decimal places, so actually 1, 2, 3, 4, 5, 6 decimal places, so that's good enough for us. 0.00308. All right, and so number 6, this ends up being our p-value is 0.003085. And so in number 7, since p is less than alpha, in this particular instance it's 0.003085 less than 0.01, we will reject the null hypothesis. All right, and then number 8, we're going to interpret this. So since we're rejecting the null hypothesis, let's go all the way back up to here. Our claim is in the alternative hypothesis, and since it's in the alternative hypothesis, we're allowed to support or not support. And so since the p-value, p equal to 0.003085 is smaller than 0.01, the null hypothesis must be rejected, and thus there is statistical evidence to support the claim that the mean pit stop time is less than 12 seconds. All right, and so we did all that, and so as a practical matter, we went through and we made all these calculations. But in the quote-unquote real world, we can get all of this stuff fairly easily. If we go no, we don't need to go second. If we go to stat and we go over here to tests, this was a z-test. So if I hit 1 for my z, and we go through and we talk about how to enter this stuff. So our proposed mean, our null mean, we said was 12, and then our standard deviation was 0.02. We have a sample mean of 11.9, and the number of elements in our sample, I think, was 30. Let me check here my notes just to make sure. Yep, was 30. And so is the mean that we are calculating, is it, and this is you go to your null statement to do, or your alternative hypothesis. So we want, is the mean is the actual mean less than that proposal. So when we go to plug it into here, we definitely want that less than. And so I come over here to calculate. And after I've calculated all of this stuff, we can see, there's a mistake there. Let's go back in here, test. What did I do wrong here? There's a mistake. There it is. The standard deviation was not 0.02, it's 0.2, so let's delete that. All right, sorry for the mistake. I'm sure you guys all saw it, but here we go. We can see that for our mean less than 12, that's again our alternative hypothesis, we get a z-score of negative 2.7386. That's what calculated. We have a p-value 0.03085. Got that. And so again, the z-test here isn't going to change depending upon what your significance level is. Your significance level determines whether you reject or fail to reject. So this one, even at the 0.00 levels, it wouldn't matter if it was 0.05 or the 0.1 level, we would be rejecting the null hypothesis in all instances. All right, so let's go down here. According to a study, the mean cost of hair augmentation surgery, hair plugs, is $10,500. We believe this information to be incorrect. 20 hair plug recipients randomly chosen at the mean cost of hair plug surgery of the sample turns out to be $11,013.43. For past studies, the population standard deviation is known to be 1,576, and that the population is normally distributed. Is there enough evidence at the 0.05 level to reject the claim? All right, so we go through again. We're going to do all of the steps. So one, we have to verify your assumptions. In this case, our standard deviation for the population was 1575, and even though our n is equal to 20, we have a normally distributed population. T-I-O-N. There we go. And so we don't need that n to be over 30 because the population is normally distributed. And so number two, our claim is, let's see here, our claim is hair plug. Actually, let's do it this way. The mean hair plug surgery is 10,500. And so our null hypothesis is going to be mean equal to 10,500. And so our claim this time is in the null hypothesis. And our alternative hypothesis is not equal to. And so this implies a two-tailed test. All right, so we gotta be careful there because we're gonna split our area up into two parts. And so number three, our significance level is alpha equaling to 0.05. And remember, since this is a two-tailed test, just real quick, that means here we're putting in 0.2 or 0.025, and over here is again 0.025 and of the area. And so the z-scores, if we were just going, so our critical z-scores would be at 0.025, and you can calculate that fairly easy. We'll edit it. And so if we wanted to do that, instead we'll do the inverse norm. The area is 0.25. All the remaining stuff stays the same. And so I don't know why I did that. All right, and so what we'll do here. Okay, so what we'll do here is we'll go second, and then we'll go distribute, and we're going to do inverse norm. So 3. We want our area to be 0.05, and there's our there's our ZC. So go back to here. It's negative 1.9600. That's the negative one, and then a positive one. Again, symmetry, 1.9600. All right. And so number 4, we'll find our standardized test statistic. Z again is going to be x bar minus the mean over the standard deviation over the square root of the number of elements in the sample. And so for this particular one, we've got, we said it was $11,013.43, and they're claiming that it's 10,500, and that'll be all over the 1,576 over the square root of 20. And just for time's sake, I've already got this calculated. It turns out to be 1.456 and so a couple of different things. If we're doing by region, we could say that 1.4569 is inside here, and so since it's inside, we're going to fail to reject. But we can also find the p-values, so the area. And so if I wanted to do that, we could go second, and then we could hit that normal CDF, so 2, and we can go from negative infinity to that, or well, actually, this one is going to be on the right-hand side because, and again, that it's that 1.4569, where I guess we'll be kind of looking that way. So this particular instance will start on the left, 1.4569. The upper will be positive infinity, 10,000 is good enough. And second entry, oops, no, don't do that. 0, go down, we'll hit paste. And now this is only half the p-score because again, it's only half the p-value. So the area, normal, CDF, and then we'll go 1.4569 comma 10,000 comma 0 comma 1, and we ended up with 0.0726. Now again, that's the half, and so we have to multiply by 2. So the p-value is actually going to be equal to 2 times. And that turns out to be, this is number 6, by the way, sorry, got ahead of myself. This turns out to be 0.1452. All right, and so if we keep moving on, 7 here. Since p is greater than alpha, in this particular case 0.1452 is greater than 0.05, we will fail to reject the null hypothesis. So in 8, all right, that means there is statistical evidence at the let's see, alpha equals 0.05 to fail to reject CT the claim that the average price for hair plugs is $10,500. All right, and again, because the claim, let's go all the way back up here, because the claim is in the null hypothesis, we can't support or not support. We either have to reject or fail to reject. And so that's how I come up with that. And that's all I got for today, folks. So here's the Marvel fun fact of the day. Carol Danvers has not always gone by the name Captain Marvel. In the comic books, she's also gone by Ms. Marvel, Warbird, Binary, in different iterations of the character. That's all I got. Have a good day. Bye.